This talk is about refuting the dream XOR lemma via obfuscation and resettable MPC. This is joint work with Saikrishna, Yuval, Amit and Daniel, and Yuval and Daniel are in the audience. So let me just start out by telling you about what the XOR lemma is trying to do. It's about the amplification of hard predicates. And in particular, a predicate over some distribution is going to be epsilon hard for the purposes of this talk if for inputs drawn from that distribution, the output of the predicate applied to an input cannot be predicted by PPT adversaries, given Y, with probability better than half plus epsilon, where one could imagine different notions of epsilon that correspond to different notions of hardness of predicting the output of the predicate. So epsilon could be a constant, or even even 1 by p, or even inverse polynomial for some polynomial p. Or one could imagine a stronger notion where one might want that the equation above hold for all epsilon that are inverse polynomials. Or one could ask for something even stronger, which says that the equation above holds for a specific negligible function epsilon. And so one of the things that we've tried to understand for many years now is, what sort of hardness holds for different types of predicates. And in particular, the XOR lemma considers predicates that are computed as the XOR of a predicate computed on many different inputs. So in particular, take an input, take predicate P that applies to n bit long inputs, and compute predicate P XOR that applies to n square bit long inputs, where your n square bit long input is divided into n bit long inputs, and you apply the underlying predicate P to every chunk in your input and XOR the results. And how hard is this predicate P XOR relative to the original predicate P? And so that's sort of the question that the XOR lemma tries to address.
Assuming a product distribution of Ys, right?
Yes. And indeed, assuming that the Ys are all independent. And so for a one-way function f, a hardcore predicate P is for a one-way function is a function that's efficiently computable given the input to the one-way function x, but hard to predict given the output of the function, which is f of x. So many of us must be familiar with this notion of hardcore predicates for one-way functions. And this question of amplification of hardness of hardcore predicates was first asked in the context of one-way functions in presentations by Yao. And again, here you could imagine defining a new one-way function g that on input x1 through xn that are all independent random from the distribution of f outputs the result of applying f to each of these n inputs. And one could ask how hard is the hardcore predicate for g, which is defined as the XOR of the hardcore predicates for the function f applied to each of x1 through xn. And there's now a stark gap between what we can prove and what we think intuitively should maybe be true. So what we can prove is that if P is epsilon hard, then the P XOR predicate is epsilon to the n plus negligible in K hard, where K denotes the size of these inputs, these individual inputs, xi. Ideally, we would like to say that if P is epsilon hard, then P XOR is epsilon to the n hard. And we would want this to hold for every n, for example. And there's a big divide, actually. One could wonder if there are intermediate statements that are true, saying that if P is epsilon hard, then P XOR n is maybe only slightly inverse superpolynomially hard. So like k to the minus log k hard. And there's some n. So if you repeat it sufficiently many times, polynomial in k, of course, then it gets harder than arbitrary negligible And you can actually pin down a specific negligible function such that it is hard for that particular specific negligible function. So, and so for the purposes of this talk, this statement is what we will call the dream XOR lemma. So if P is epsilon hard, then P XOR, we'd like to understand if P XOR is k to the minus log k hard for some large enough n equals poly k. Any questions about the? So, it was realized many years ago that proving this type of a lemma, even for like small negligible functions like k to the minus log k, is, or sorry, bigger negligible functions, is going to be hard. And the reason is that one would want that there exists a reduction that break a weakly unpredictable hardcore predicate, given access to an adversary that breaks the strongly unpredictable hardcore predicate. Now, the problem with doing this is consider an adversary that with probability 1 minus this negligible value outputs random things, so does nothing interesting. And with probability, this small negligible value actually does something interesting and predicts the output of the hardcore function. Now, a reduction that's interacting with such an adversary would have to run this adversary something like k to the log k times to even get an interesting output, but it cannot, since all of this was for PPT adversaries. And so Rudik was the first was first to realize this, and in fact used this to get an oracle separation. I'll tell you a little bit about what that oracle looks like later on, but I also want to point out that there were subsequent works by Schaltel, Grinberg, Schaltel, and Viola, and then more works more recently that showed that natural types of proof techniques cannot possibly prove the dream XOR lemma. Again, I won't get into what they ruled out. Our goal in this work is to actually obtain an explicit counterexample to the dream XOR lemma stated here. So we'd like to understand if there exist any explicit constructions of one-way functions for which the hardcore predicate does not amplify when repeated many times in parallel, and the predicate XOR. Okay. So this is closely related to the dream direct product theorem for amplifying the hardness of one-way functions. So for a one-way function, you can define the n-wise direct product of the function as just the output of the function computed on n different inputs and appended together. Now, how hard, sorry, this should have been n. How hard is this n-fold direct product? Well, if f is epsilon hard, then again, we can prove that this is epsilon to the n plus negligible in k hard. And it's really this negligible in k term that's annoying. Ideally, we'd like to be able to go here and say, you know, if you repeat n equals k times, then you get something like 2 to the minus k hardness. And maybe it is true that if f is epsilon hard, then again, there's an intermediate statement that could hold, which just says that the n-wise parallel repetition, or this again should have been n for large enough n equals poly k, that this is at least somewhat, there's an explicit negligible function that we can pin down, and that this is at least that hard. So not just saying that this is arbitrarily negligibly hard, but pinning down this explicit negligible function. And again, we don't know if this is true for any function. We don't know if this is true for all functions. Sorry, we do know that this is not true for all functions under certain contrived assumptions. And so this was a result by Dodis, Jen, Moran, and Wichs, who showed that the dream direct product theorem is actually false by constructing a weak one-way function whose hardness does not amplify to this value, assuming some properties of unkeyed hash functions. And I won't get into the specific properties, but they showed that these properties hold in the random oracle model, and they used that to justify this assumption. So, yes.
Even the one talking to the maybe.
Yes, yes. So no, it's not true under this assumption. So what I was saying is, okay, well, maybe is a little bit misleading, I guess. I'm trying to point out that there's like different levels of hardness one could ask for, and this is an intermediate level, and we didn't know if this was true or not. But under the assumptions in this work, which assumes a certain property of unkeyed hash functions, we know that this is actually false for, like, there is one-way function for which this is false. Okay, so our results are the following. We show that in the ideal obfuscation model, assuming sub-exponential DDH or LWE, there is an explicit injective one-way function such that the XOR of the n-fold parallel repetition, the XOR of the hardcore bits of the n-fold parallel repetition can actually be predicted with k to the minus log k for every n that is polynomial in k. So for every large enough n that's polynomial in k. We also show that assuming PCDIO and this assumption called extended second preimage resistant hash functions, which is the same assumption as in the Dodis et al. Work, injective one-way functions, there exists an explicit injective one-way function such that the XOR of the n-fold parallel repetition can again be predicted with this probability. So this is basically obtaining counterexamples under two distinct classes of assumptions. And the first one is more relevant for this talk. So I'm going to focus on that first result for the rest of the talk. Yes. Good. Yes. Sorry. So yes, this was for the dream direct product theorem. It says that the direct product of n-fold parallel repetitions of one-way functions. This is not about the XOR of the hardcore predicates. And yes, thank you. Actually, I meant to say that. Indeed, if this dream direct product theorem for one-way functions was true, then the dream XOR lemma would also be true. But this is a counterexample to the dream direct product theorem. And in particular, this counterexample does not consider injective one-way functions. So if the one-way functions they used were injective, then it would easily extend to a counterexample to the dream XOR lemma. But because their one-way functions are not injective, that means inverting those one-way functions means you find some preimage, and it may not be the right preimage that lets you predict the right hardcore pair. So thank you for asking that. I forgot to say that. So yes. Yes, it does. Our result implies the direct product result, but it was already known in some way. Not under the first set of assumptions, but under weaker assumptions than the second set. Okay, so now let me get into the technique that we use. So let's recall from this impossibility that if there is an adversary A that with a good probability does nothing interesting, and with a small probability completely like predicts your hardcore predicate, then it's going to be hard to use that adversary. So this gives us an idea, like what if we create a bad event that allows the adversary to predict, and this bad event occurs with the small probability. And to do this, we will introduce an all-powerful oracle that inverts all one-way functions with probability k to the minus log k. And so this was actually Rudick's idea. Now, ideally, again, we would not want an oracle separation. Our goal is to get an explicit one-way function family for which hardness is not amplified. And so we would like a separation without this oracle, and also where the one-way function instances are completely uncorrelated. So we don't want to assume a CRS, for example, because that could introduce correlations and such. And so our idea is let's distribute the oracle. So what I mean is let's do an MPC. And bear with me for a second, because when I say this could be a little bit confusing in the beginning. But in cryptography, there is this technique of implementing a secure multi-party computation protocol between independent players that can implement arbitrary ideal functionalities. So the ideal functionality that we will implement is going to be a one-way function. Is going to be the inverter of the one-way function. Again, it may sound like this is inefficient, but bear with me. And this inversion is only going to work with probability k to the minus log k. So this ideal functionality will toss coins. And with probability k to the minus log k, we'll completely invert everything. And with the remaining probability will not give you anything interesting. It'll output bottom or something. Now, there's a bunch of problems here. First, we want to build one-way function counter examples. One-way functions are a non-interactive primitive. MPC is an interactive primitive. So this is where we use the ideal obfuscation model. We embed the next message function of MPC players into a program that we obfuscate. And this obfuscated program becomes our instance of the one-way function. So in more detail, the one-way function on input some x is going to instantiate with like randomness x a new player in an MPC protocol and obfuscate the next message function of this player. And that's going to be our description of the one-way function. And now the second problem was this oracle it seems like it's doing an inefficient task, but one-way functions should be efficiently computable. Moreover, we want our break of security to also be efficient. But the point is, all these one-way functions actually know their own input. And so what I mean is P1 represents the output of a one-way function evaluated on input x. And so what one can do is hardwire x into this obfuscation so that when all these players run an MPC protocol, each player actually has their x hidden away in their obfuscation. And if this bad event occurs, then the MPC protocol ends up revealing all their inverses, and otherwise everything remains hidden under ideal obfuscation. So that's roughly the idea here. And see, now there's a few problems. The first is that each individual one-way function, which itself is an obfuscated party running an MPC protocol, should be proven secure. And in particular, an adversary, for example, can take this obfuscated party, it's just the output of a one-way function, query it many, many times. And recall I said that the inverse x is hidden somewhere in this code. So maybe query it out of order for the MPC, and that may help the adversary to recover the inverse x. So we want to defend against that. And that requires us to build multi-party computation protocols that are secure against attacks that can be made out of order. So even in the ideal obfuscation model, this takes some work because MPC is a stateful functionality, whereas these are all stateless programs. So we resolve this by building a resettable MPC protocol with, for technical reasons, we need super polynomial simulation guarantees in the MPC. If you don't know what this is, don't worry about it. It's a technicality related to some impossibility results for polynomially simulatable resettable MPC. So we build this object, and then using such a resettable MPC, our one-way function instantiates each of these instances by obfuscating the next message function of a party that runs this protocol. Sorry. And so that finishes actually an overview of our counter example construction. In conclusion, in the ideal obfuscation model, we obtain a contrived counter example to the dream XOR lemma. And this is actually this can actually be made an explicit heuristic counter example by instantiating ideal obfuscation with a candidate indistinguishability obfuscation scheme. Prior to our work, even heuristic counter examples were not known. Let me also just mention that, by ideal obfuscation model, just like this is something Yuval also talked about yesterday in his talk, this model simply can also be instantiated with stateless hardware tokens. So you can embed this functionality into hardware tokens, but you can also obtain heuristic counter examples that do not involve any hardware by relying on candidate obfuscation schemes. So with that, let me conclude and leave you with some open problems. The first is, do hardcore predicates of natural injective one-way functions amplify? So we have a very contrived counter example that's running an MPC inside of an IO, and doing this, like creating this very special bad event. Can we come up with more natural examples that amplify? That either amplify or do not amplify. Like we don't have proofs of amplification for simple candidates. We don't know whether they don't amplify. So where is the boundary? What are the class of functions that amplify? Which ones don't? And then can we obtain counterexamples under better studied, more standard assumptions? Thank you, and happy to answer any questions. Yes.
Oh, dangerous.
So continuing your first open question, so can you kind of somehow argue that the failure of the dream XOR lemma implies something non-trivial and therefore maybe useful? And I don't know, like for example, like some sort of public key assumption, and therefore, even if we believe that public key assumptions exist, maybe if I just use, I don't know, some SHA function or some simple hash function, I'm not expecting to extract from it a public key encryption, and therefore it's plausible that it satisfies some sort of dream XOR lemma. So
It's a good question. I'm not, so I have examples of where proving the dream XOR lemma for certain types of one-way functions is helpful. For example, there's constructions of non-malleable commitments that rely on unproved hardness amplification assumptions about like natural one-way functions. For all we know, those hold. And so for all we know, under DDH, these types of non-malleable commitments that are completely non-interactive should exist. But failure of the dream XOR lemma, I haven't thought as much about. I don't know if maybe Yuval or Daniel have insights.
For the direct product, the counterexample is just based on the hash function property, so you wouldn't expect that to give you public key encryption. I don't know about the XOR.
Other questions?
Can I ask a question from Zoom?
Oh, yeah, go for it.
So do your techniques also rule out direct amplification, direct product amplification of distributional one-wayness?
Question. I think they can be extended too. Like we didn't. I think you could extend it so that the bad event occurs. So when the bad event occurs, you output actually, I'm not sure. Like you might want to output a random pre-image instead of the one you started out with. It's unclear because it's a good question. I don't think that the ideal obfuscation one rules it out.
And then when you break it completely, then you also break it in the distributional sense, right? So
wouldn't you need to output like a
with
random
n to
pre-image?
the minus log n probability.
Wouldn't you need to output a random pre-image? And then how would you do that?
It's
if you
injective,
start?
injective. It's injective.
I see. Yeah.